Hey everyone, so let's solve today's LeetCode POTD, maximum profit from trading stocks with discounts. So the problem states that we are given an integer n, which represents the number of employees in the company, and each employee is assigned a unique ID from 1 to n, and employee 1 is the CEO. Now we are given two 1 based integer arrays, present as well as future, where present of I will be denoting the current price at which the ith employee can buy a stock today, and future will be representing the expected price at which that particular stock can be sold tomorrow. Now we are given the company's hierarchy in the form of a 2D array, which will be representing that if UI is the parent, means direct boss of employee VI, then we'll have a direct H from U to V. So this is represented by a 2D integer array hierarchy. Now we are also given an integer budget, which represents the total amount of funds that we have available for investment. Now we also have a discount policy that if an employee's direct boss purchases their own stock, that means the employee can buy their stock at half the original price. That means if one is the boss of two, then if one buys its own stock, then two will get a discount to buy his stock at half the price. Now we need to return the maximum profit that can be achieved without exceeding the given budget. Okay, so one thing is clear that we are given the 2D integer hierarchy. That means we need to form a tree here. So obviously we'll be making a tree based on the hierarchy, and now we start from the CEO, and each CEO has a choice of either buying the stock at particular day or not buying the stock, and based on whether he buys or not, we will need to means follow the constraints of the total budget and then return the maximum profit that can be achieved without exceeding a given budget. And we are also given that we can buy each stock at most once, and we cannot use any profit earned from future stock profits to fund additional investments. Okay, so hence the total number of investments that we'll be making will be from the budget itself only. We will not be adding the profit that we earn to the budget. So for this given input, let's see. So we are given two employees, 1 and 2. One is the direct boss of 2, so the hierarchy is represented by this, and the total budget that we have is 3. So if one buys the stock, its stock, so the present cost is 1 and the future cost is 4. So the profit that will be earning is 3. Now since one has bought its own stock, so to this second employee will get a discount. So this stock price will become 2 by 2, means half. So it will become 1. Now 2 can buy its own stock at 1, and we see the budget, overall budget is 3, and we have spent only one budget till now. So we have two budget remaining, and since the budget price of stock is 1 only, so we can buy it. So if we buy it, then the profit that we earn is, since he can sold it in 3 values, so 3 minus 1 will be 2. Hence the overall profit that we'll be getting is 5, and the amount of budget that we have used is 2 only, which is less than equals to 3. So hence in this case, both the employees can buy their stock, and there will be like no budget constraints here. So hence the output here is will be 5. Let's see another input. So we are given present cost as 3 4 and future as 5 8, and the budget has 4. Budget is equals to 4. Now if the first employee wants to buy the current stock, then he will buy at cost 3. So the profit that we'll be getting is 5 minus 3 equals to 2. Now for employee 2, means since employee 1 has bought the stock, so its price will become 4 by 2 equals to 2. Now since we have already utilized 3 cost, since the overall budget was 4, we will only have one budget remaining, and hence since the stock price for second employee is 2, we will not be able to buy that particular stock. Hence if we simply buy the stock for first employee, we will get a profit of 2 only. Now instead of buying the stock price for first employee only, let's try to buy for second only. So if you buy for second only, then since its cost is 4 and the budget is also 4, so since 4 is less than equals to 4, so you'll be able to buy it, and the profit that we'll be earning is 8 minus 4 equals to 4. So hence that will be the maximum output here. So how can we approach these kind of problems whenever we are given in the form of a hierarchy, and each node has a choice of either performing that particular task or not performing. So we obviously know we'll be applying dynamic programming in some form. We just need to define the DP state. But before moving on to the DP state, let's see the brute force approach. Like at each step, what are the possible transitions that we need to do, and based on that how will be like finding out the maximum value or the maximum profit. So let's see the brute force approach. The brute force approach will be like, since we have the employees from 1 till n, obviously the brute force will be considering a particular subset of these employees, which represents that these employees will be buying the stock. Now based on this, we like, let's S be a subset of employees who decide to buy the stock. So for every employee I, will be defining a variable, suppose xi, which if xi is equals to 1, that means will employee I will be buying that particular stock. And if xi is equals to 0 and I does not belongs to x, okay, so this means like this will not be belonging to s, so employee I does not buy. So this s simply means like it can be a subset of s where it will have 0 or 1 bits for each employee. If it is 0, then it simply means that it does not belong to that particular set, hence it will not buy the stock. And if it 1, that means it will be buying the stock. Okay, now once like we have created that particular mask, we need to find the cost function that will be defined at each step. So the cost for employee I will simply depend on whether their parent direct employee has bought the product or not, because if they have bought it, then we'll be getting a discount of buy 2, or we'll be buying it in full price. Okay, so let's see the cost function. So cost function will be, if xi is equals to 0, that means it simply does not belong in this subset s, so hence it will be 0 only. Now if like xi is equals to 1 and x of parent of I is also 1, that means the parent has also bought. So in that case, the present cost that will require will be present of I by 2, because we are getting a discount here. And now if parent has not bought, that means we will be paying the full price. So in that case, the cost will be present of I. Now our final goal is to maximize the total total investments that we are doing, means the total price that will be selling is future of I, and will be decreasing it the total cost that we have required. So we need to maximize this value, and along with that we need to also satisfy the condition that the total cost that we have invested should be less than equals to budget. So in this manner we can iterate through all the masks of each employee from 1 to n, and once we have a particular mask, then we can iterate through its future values and present values and calculate this value, as well as see whether like this constraint is satisfied or not. And if it does, then we can maintain a global variable which stores the maximum profit that we can have. So obviously like since creating mask of like size n will be taking order of 2 to the power n, and for each mask we will be iterating through the future or present array in n. So this will be of the order of 2 to the power n into n complexity. Let's see the constraints here. So we are given that n can go up to 160. So 2 to the power 160 will obviously not be feasible to run in 1 second or 2 seconds. So obviously we need to like optimize it to be able to run. So we know like we will be applying dynamic programming. So let's let's try to think about the states that will be following the DP. So the first the state that we can think of is at each node u, we know like either we would have reached this u by when the parent has bought it or when the parent has not bought it. Okay, so let's represent these states as 0 or 1. Means when you have reached DP node u with 0, that means its parent has not bought its stock, and if for 1 the parent has bought it. And another state that will be changing here is with what budget we have reached this u, means how much budget we have invested till we have reached u. Okay, so that is another variable that needs to change here. Hence the DP can simply be DP of root node, then the state means either 0 or 1, and then the budget that we have spent so far. And we know like the constraints. Let's see the constraints. So budget can go up to 160 only, and n can also go up to 160. So this will be like 160 into 2 into 160, which is within the range of like this is 632 24 2 to the power 9 into 1e square. So 2 to the power 9 means 1e3, so obviously it will be of the order of 1e5, which will get accepted in within limits of 1 second. And suppose for calculating this DP states we need to iterate through all the budgets, so maybe we can iterate through 160 twice as well. So 1e7 till 1e8 is accepted here. So let's see the definition of the DP state first, then we'll be discussing the transitions, and then we'll be moving on with the code. So that DP state defines as, we define a state DP U state W, where U will be it represents the maximum profit obtainable from the subtree rooted at U. Means this will be the subtree, it will be rooted at this U, and it will have some employee direct boss. Okay, we have reached this U with this particular state. State means 0 means parent did not buy, and 1 means parent did buy, so you will be paying half the price, and we have spent this exactly budget W. So, and W budget will means should remain constrained with the overall budget that we have. Okay, so let's see the transition. So transition will be either parent would have buy it. So if parent would have buy it, then we have the choice of like either buying it in half price or buying it in full price. And if the parent means or not buy at all, and if the parent did not buy, then we'll have the choice of either buying or not buying. So we have like a parent did not buy, then node U has two choices, either don't buy. So if don't buy, then cost will be 0, profit will be 0, and now since U has not buy, then its child will be seeing that his parent has not buy the stock. So hence his means for the child of U, they can have the choice of like means either means they will not be able to buy it in half the price. Okay, and now if U buys in full price, that means we'll be means calculating the cost as well as the profit, but now its children sees that his parents has buy the profit means buy the stock, since he will be able to buy in half the price. Okay, and the second scenario is simply when the parent has bought it. So when the parent has bought it, again the U has two choices, either to don't buy it or buy it in the half price. Okay, so we will be creating means calculating these two values in the same step, and again we see if it doesn't buy, then for child it sees 0, and if it buys, then the child will see the parent is stated as 1. Now once this is clear for a particular U, we need to be able to, for all the means child node V's that it has, we need to be able to know like with what budget he was able to calculate this value, and with what budget we have reached. Suppose we have reached here with W1 and reached here with W2, then we need to make sure that while we merge these two states, this overall budget still remains means less than or equals to the constraints that we have. Okay, less than or equals to the overall budget. So while merging, we need to ensure like we will definitely need to merge these two states of U and V, and then we also need to ensure that the overall budget still remains in the constraints. So let's see the merging part here. So if DP current of W means with W budget we have reached node U. Okay, before considering previous children. So if we have reached U with budget W, so this will be stored in suppose this DP current of W, which can W will be size at most of size 160. Okay, so this is DP1, and we have the DP child DPV, which is suppose DP2. This will also like it has expended K means K profit. Okay, so it has utilized K budget, and this will also be a DP of size 160, means for all costs from 0 till 160 will be storing it. Now DP child of K be the max profit for child V using budget K. So what will be the new DP for this U with budget W? So it will be simply like, since we are using child DP means child with K budget, so the new budget remaining for U will be W minus K. Okay, so hence the DP new of W will be simply max means will be taking maximum at each step, so it will be simply DP current of W minus K, and the child has utilized K budget. So this is how we'll be means defining our transitions, and obviously like since we are merging it, so we need to iterate through all possibilities for this W, which can go up to 0 till 160, and this K can also go from 0 till 160. So this overall merging step will be of the order of B square. Okay, so this will be the like the merging of two budget arrays of size B takes B square. So this is how we'll be defining a DP, and then we'll be defining our transitions, and then just like we'll be like calling the DFS function to calculate these two DPs at each step. Means either means we definitely need two DPs at each step. What do we need? We need suppose vector LL comma vector LL. So we need a pair of these DPs at each node. Why? because this will denote that suppose parent did not buy, parent did not buy, and this vector LL will denote that parent did buy. Okay, and now for each node we need to calculate both of these DPs that we have reached U with either parent buy or parent did not buy. And then on the basis of that, at each step we'll be calculating these two DPs for each node by calling the DFS for its further childs, then doing the merging part, and then returning the vector such that it restores the maximum possible results. Okay, so like the code is pretty like messy here. Let's see it step by step to get a clear understanding of it. So we have like this was the main function that we are given. So I have initialized all the variables as global here so that we do not need to pass it add references in each of the functions. Now we are given like int n, this present, future, as well as the hierarchy and the budget. So we initialize all the values with the values that we are given. Now we build this adjacency for the given tree. So we have declared this adjacency global as well. Now we'll be iterating through the hierarchy and building this tree. So we'll build this adjacency list of size like n plus n cross n. Now we iterate through each edge, and for u we have the v as employee. Okay, so there will be an edge from u to v. Now we start the DFS from CO employee 1, and since CO has no employee, so we means each DFS will be returning this pair vector of LL comma vector of L. So this first denotes that its parent did not buy, and this first means a second vector represents that his parent has bought the stock. So for calculating the maximum result, we will see that for the CO employee 1, there exists no parent, so hence it will fall in the parent did not buy category. So hence the maximum value is calculated from root, means a root result dot first value. Okay, so we'll be calculating this maximum result and finally returning it. Now the main step is to see how this DFS function progresses. So let's see the DFS function. We'll be means following the step-by-step approach that we discussed of the transitions, and at each step how many possible scenarios that we have. So this DFS returns a pair of vectors. Means first will represent the DP table if current node's parent did not buy, and the second will represent that DP table if current node's parent did buy. And this vector means both vectors can go up to size buzzer. Okay, now the base cases will be like the first case will be to you did not buy. So you did not buy, that means it will be simply means the cost is 0, profit is also 0. Okay, now second is you buys. So if you needs to buy, then it is dependent on parent, whether like parent bought it or not bought it. So if parent did not buy it, then you will be paying the full price. So the cost full will be present of u minus 1, since u v all are means 1 based, and since to access the cost of u, it will be present at index u minus 1. Hence the profit full will be future of that particular stock minus current cost. And hence we'll be updating this DP full by of like if the cost that we have is less than equals to limit, is still less than equals to limit, then it will be simply profit. And the second case is parent did buy, so we'll be able to buy in half the price. The current cost will be present of u minus 1 by 2, the profit will be calculating, and for this will be initialize this DP. So these two DPs means we have currently have three cases: this DP no buy, this DP full buy full, and this DP buy half. Now based on these we'll be like returning two vectors. First will be which will be like parent did not buy, so it will be like either DP no buy or like parent did not buy, so DP buy full. And for parents buy will be DP buy half. Okay, so now comes the merging step. At merging step we have the child result, we have got the child we'll be calling in the DP for DFS for child node, and then we'll be getting some result. Now if u has not buy it, we also need to account that case where u has not buy it. So based on that, it will be stored in like children will see like parent bought equals to false, so it will be stored in first this. So we'll be needing to call the merge function for DP no buy as well as this child result dot first. And if u has bought it, then children will see that parent has bought, so this result will be stored in vector means the second one. So we need to means merge it for both the cases where it buy full or it has bought half. Okay, so we'll be calling the merge function for both of these values. We'll be seeing the merge function. It will be simply what we discussed previously. This is the merge function that we are using. for each, means it will be doing merging in big of B square. We'll be going through all possible budget limits constraints for both the nodes and then calculating it. Now once we have, means perform the merge operation, these dp no by, dp by full and dp by half will be updated. So now based on these we need to like return these two vectors of parent by parent bought or parent did not bought. So we iterate through all, means from for this current dp we will be calculating these two values at each step. So if parent did not buy, you could not choose not to buy or buy full. So it will be 0 of b will be maximum of both these values, dp no buy and dp buy full. And if parent bought, then it will be dp no buy or dp buy half. So at each step will be, means taking maximum to store the maximum possible values in both these vectors, and it will be simply returning these two vectors. Now talking about the merge function. So merge function will be nothing but we will be going through all budget limits for both the for the both the nodes, and then we'll be like updating the dps. So we have two dps, the target which belongs to the parent and the source which will belong to the children. Okay, now we perform the merge. So we perform the merge, we iterate through all possible limits for budget b, means for the parent, and well as the splits that we can have for k. So for k it will be k, so for parent it will become w minus k. Okay, so it will be like k. So if target b of b minus k, initially we have initialized it with -1, so means with a very small value, so that we are able to see whether that particular state is already calculated or not. And if that state has already been calculated, then only we will be taking the maximum. So if both of these values are not, means a minimum, then we'll be updating our next target with the same dp state that we talked. It will be what, maximum of dp of current of w minus k plus dp child of k. Okay, so target of mu minus k plus source of k, and then we'll be updating our target with the next target, because we have updated our like the target node which belongs to the root node with the new updated dp after merging. So this was the overall approach for this problem. Let's see the time complexity as well here. So we see like this building adjacency will be taking in, since we are going through the budget array, so the number of edges that we have here. Let's see the constraints. So the number of employees that we can have here is n only, so we'll be having big of n. And now we need, let's see the time complexity for this dfs. So this dfs will be taking, at each step we are doing, means iterating through each employees, and for each employee we are doing the merging part. So it will be big of n into limit square, and since n can go up to 160 and limit can also go up to 160, so it will be 160 cube, which will be like 2 to the power 9 into 10, 2 to the power 160 to 2 to the power 4 into 10 ka cube. So 2 to the power 12 into 1e3. So it will be obviously of the order of 1e6. So this will be like the most acceptable approach for this problem. Let's try to submit the code as well and see whether it runs or not. So this is the same code that we discussed. We call the dfs function and then the merge function at each step. And we see like it runs in 506 ms, which is pretty fast for these kind of problems. So I hope like you are able to see at the first step only, like we have a choice of either getting, means either buying or not buying at each step, and from that we derive that we will be using dynamic programming here, and then just defining the dp state as well as the transitions was the main part. And once we have did that, then like implementation can vary on the basis of how you try to implement it. Or means instead of like returning these pairs from dfs at each step, we may have maintained a global dp and then try to like update its value. So both are fine here. So I hope you were able to follow along, and if you did, make sure to like, and if you have yet any doubts remaining, you can comment down and I will be happy to respond. Thank you so much for watching.